This presentation is on calculating and interpreting a four-cell chi-square statistic. Recall from the previous podcast that the formula for calculating a two-cell chi-square statistic is the sum of the observed frequency minus the expected frequency divided by the expected frequency. This formula is the same for a two-cell and a four-cell chi-square. It is in the expected frequency calculation that things differ. The expected frequency in a two-cell chi-square is simply half of what the total number of cases is in the problem. The hypothetical survey example from the last podcast of Smith versus Jones voter support with n equals 200 meant that the expected frequency is what we expect the frequency to be if the null hypothesis is accepted, or no difference at all between the two candidates in voter support, 100 versus 100. In a four-cell chi-square, we might believe that all we have to do is assign an equal number of cases to each cell and call that the expected frequency. Sometimes that will work, sometimes not. Let's take up three examples of four-cell chi-square to see how we assign expected frequency, calculate chi-square, and interpret the results. In four-cell chi-square, subjects are classified in two ways. In our first example, the support for our two candidates, Smith and Jones, is broken down by gender. 120 male respondents support Smith, and 80 male respondents support Jones. Conversely, 80 female respondents support Smith, and 120 female respondents support Jones. Is there a statistically significant difference between the genders in the way that they evaluated Smith and Jones? We need to calculate expected frequencies for each cell. This is a simple activity. The expected frequency of each cell is equal to the row total times the column total divided by the total number of cases. So here's how this expected frequency calculation works. Male respondent Smith is cell 1. Female respondent Smith is cell 2. Male respondent Jones is cell 3. Female respondent Jones is cell 4. For cell 1, the row total is 200. The column total is 200. 200 times 200 is 40,000. Divide that by the total number of cases, or 400. We find the expected frequency for cell 1 to be 100. In fact, we see that for each cell, since the row total and the column total always multiply to 40,000, the expected frequency is always 100 for each cell. Recalling that the chi-square statistic is the sum of the observed frequency minus the expected frequency squared divided by expected frequency, we simply do the calculation. 120 minus 100 squared divided by 100, plus 80 minus 100 squared divided by 100, plus 80 minus 100 squared divided by 100, plus 120 minus 100 squared divided by 100. 20 squared divided by 100, plus minus 20 squared divided by 100, plus minus 20 squared divided by 100, plus 20 squared divided by 100, yields 400 divided by 100, plus 400 divided by 100, plus 400 divided by 100, plus 400 divided by 100. 4 plus 4 plus 4 plus 4 equals 16. For df equals 1, the critical value is 3.841, and we reject the null hypothesis of no significant difference between Smith and Jones in terms of their genderized vote. There is a gender gap between Smith, who is favored by male respondents, and Jones, who is favored by female respondents. Let's examine a second example. A few years ago, a colleague and I surveyed all county elected officials in Idaho. We asked for the elected officials' views on issues, including the death penalty. We found the following measurements of support of or opposition to the death penalty, broken down by political party. Notice that the overwhelming majority of county elected officials favored capital punishment, but is there a difference between the county elected officials on their capital punishment views based on their partisanship? Our first task is to calculate the expected frequency for each of the 4 cells. Row total times column total divided by total number of cases. Democrat opposed capital punishment is cell 1. Republican opposed capital punishment is cell 2. Democrat favor capital punishment is cell 3. Republican favor capital punishment is cell 4. Or, for cell 1, 21 times 64 divided by 228 is equal to 1,344 divided by 228, or 5.89 expected in the top left cell. For cell 2, 21 times 164 divided by 228 is 3,444 divided by 228. 15.11 is expected in the top right cell. For cell 3, 207 times 64 divided by 228 equals 13,248 divided by 228, or 58.11 expected in the bottom left cell. For cell 4, 207 times 164 divided by 228 is 33,948 divided by 228, or 148.89 expected in the bottom right cell. Recalling that chi-square statistic is the sum of the observed frequency minus the expected frequency squared divided by expected frequency. 12 minus 5.89 squared divided by 5.89 plus 9 minus 15.11 squared divided by 15.11 plus 52 minus 58.11 squared divided by 58.11 plus 155 minus 148.89 squared divided by 48.89. 148.89, excuse me. 6.11 squared divided by 5.89 plus minus 6.11 squared divided by 15.11 plus minus 6.11 squared divided by 58.11 plus 6.11 squared divided by 148.89. 37.33 divided by 5.89, 37.33 divided by 15.11, 37.33 divided by 58.11, 37.33 divided by 148.89, 6.34 plus 2.47 plus 0.64 plus 0.25 equals 9.70. df equals the number of rows minus 1 times the number of columns minus 1. So df equals 1. For df equals 1, the critical value of chi-square is 3.841, and we reject the null hypothesis of no significant difference between political party affiliation and support for capital punishment. Let's look over a third example. Does a primary commodity exporting country have a lower GDP per capita than does a non-primary commodity exporter? World system theory suggests that primary exporters do score lower on GDP per capita. Briefly, world system theory is that nation-states that were colonized by major European powers such as Spain, Portugal, France, Germany, and the UK were exploited by those countries and made to give up raw materials as primary commodities to their colonial masters. The colonial powers either kept the treasure or used it to manufacture value-added goods that commanded more profit per unit, leaving the peripheral colonized countries in a perpetually disadvantageous position vis-a-vis core colonizing countries of Europe. Can world system theory help explain variation in GDP per capita? We need to calculate expected frequency. For cell 1, 56 times 76 divided by 112 equals 4,256 divided by 112, 38 expected in the top left cell. For cell 2, 56 times 36 divided by 112 is 2,016 divided by 112, or 18 in the top right cell. Expected. For cell 3, 76 times 56 divided by 112 equals 4,256 divided by 112. 38 is expected in the bottom left cell. For cell 4, 36 times 56 divided by 112 is 2,016 divided by 112. 18 is expected in the bottom right cell. Recalling that chi-square is equal to the sum of the observed frequency minus the expected frequency squared divided by the expected frequency. 26 minus 38 squared divided by 38, plus 30 minus 18 squared divided by 18, plus 50 minus 38 squared divided by 38, plus 6 minus 18 squared divided by 18, minus 12 squared divided by 38, plus 12 squared divided by 18, plus 12 squared divided by 38, plus minus 12 squared divided by 18. 144 divided by 38, plus 144 divided by 18, plus 144 divided by 38, plus 144 divided by 18. 3.79 plus 8, plus 3.79 plus 8 equals 23.58. The DF is equal to 1. Again, the critical value for 4-cell chi-square is 3.841, and we reject the null hypothesis of no significant difference between primary commodity exporters and non-primary commodity exporters in terms of their GDP per capita. World system theory seems to apply to this example. This concludes our presentation of the 4-cell chi-square statistic.